So welcome back to our discussion about circuits. We learned a little bit about some important considerations for digital circuits in the last lecture. In this lecture, I want to discuss just a few key considerations for analog circuits. So we're going to be looking at applications where we're taking a small time-varying signal and trying to boost it into a much larger version of itself. Now, there are a lot of applications for analog out in the world. Many of the natural signals that we want to sense with various electronic sensors are just naturally analog. A lot of the signals that we read in things like disk drive electronics, where we want to convert them to digital signals, are really analog signals when we read them. And there are other applications in optical receivers when we're sending messages down fiber optic communication channels. A lot of analog signals that need to be processed, oftentimes converted into digital signals. Now, CMOS technology is a good technology to implement analog functions. If you were only going to implement analog, actually bipolar transistors are a better device for doing that. But many systems are both analog and digital, and they will have a lot of digital electronics in them. CMOS is the dominant technology for digital electronics. So there's a lot of incentive then to try to make use of CMOS also for analog. And over the last several years, CMOS performance, analog performance, has increased to the point where you can do quite a lot of CMOS analog without having to resort to bipolar transistors. You know, there are special applications. The highest frequencies and highest performance applications are often done with bipolar, but quite a lot can be done with CMOS. So let's talk about the basic common source MOS amplifier. So here's an N-channel transistor. The input is to the gate. The output is from the drain. The drain is connected through a resistor to a power supply, and the source is connected to ground. Very simple circuit. The output is taken from the drain. And we have at the input a DC voltage that's going to bias the transistor at some good operating point. And then superimposed on top of that is a small AC signal that we're trying to amplify. So the output voltage will also have a DC component and a small time-varying AC component. Same with the current. The current will have a steady-state DC component and a small time-varying AC component. We're interested now in this AC time-varying component. So the DC current is a function of the DC voltages across the device. The AC current, is a function of the small signal voltages across the device. So it makes sense to write, we will write the small signal AC current as proportional to the small signal voltage that we apply at the control terminal between the gate and the source. The constant of proportionality is G sub m. We call it transconductance. Transconductance because it relates an input voltage to an output current. All right. Now, what is that transconductance? Well, we just solved that equation. That's the small signal current in the drain divided by the small signal voltage we apply at the gate terminal. Well, that's small signal. That's like a small delta in the DC current. A small delta ID divided by a small change in the input DC voltage between the gate and the source. So if that increment is small enough, then that's just the derivative. The derivative of the DC drain current with respect to the DC gate to source voltage at a fixed voltage up between the drain and the source. Now, this works. You may say, well, I have time-varying signals. How can I use my DC IV characteristics to describe the time-varying signals? And the point is we can do this as long as the frequency is not too fast. As long as the device can keep up with the frequency, then this so-called quasi-static approximation works quite well. So we have a definition of the transconductance of the transistor. It's the derivative of the drain current, the output current, with respect to the gate to source voltage, the input voltage, at a fixed drain to source voltage. And this is an important parameter because it's a measure of the function of a transistor to provide gain and amplification. We can see that in this little amplifier circuit. So now I'm only showing the small signal AC parts. I'm only showing the small signal voltage at the input, and we're only interested in the small signal voltage at the output. We're solving this by superposition. So I'm taking all of the DC power supplies, the power supply up here, and I'm grounding it because AC-wise it acts like a ground. We're only looking at the small signal part of that now. And if I ask myself, what current flows, what's the output voltage? You can see that the output voltage flows through this resistor RD, and we develop a voltage there. We're taking the output voltage at the bottom of that resistor where the sign is negative. So the output voltage is minus G sub M times the value of that drain resistor, R sub D, times the input voltage V in. All right. I'm going to be interested in the voltage gain. How much bigger is the output voltage than the input voltage? So I'll just take the ratio of the output voltage to the input voltage, and you can see it's minus G sub M RD. The minus sign means that there's a 180 degrees phase shift between input and output, but the magnitude is determined by the transconductance times this resistor in the drain itself. So transconductance is a very important figure of merit for a transistor because it tells us how much amplification we can get out of a circuit like this. It's a measure of the ability of the transistor to amplify a signal. So it's a key parameter for an analog application. Now, one of the questions that designers would ask is, if I'm very clever and design very sophisticated amplifiers, what is the maximum gain I could ever achieve using this transistor technology? Well, there are ways that designers have where we can implement almost ideal current sources that have nearly infinite small signal resistance. So it's effectively, we're making that drain resistor in the previous circuit infinite. All right, that wouldn't work for the DC biasing of the device, but if we implement this with a current source, then small signal wise, we can essentially have an infinite resistor there. And then the question that we have is, what is the gain? Well, the gain isn't infinite because we have to look in a little more detail at the transistor. Okay, so to answer this question, let's look in a little more detail at the transistor, but just to back up for a second. If I have an IV characteristic like this at some fixed gate to source voltage, VGS1, and then if I add a little delta V to that gate to source voltage, I'll get a little more current. All right, and that little more current will be proportional to the increment in the gate voltage. And that constant of proportionality is what we've called the transconductance. Okay. Well, if I also look at this IV characteristic, and if I'm biased at a particular voltage between the drain and the source, I'm not going to change the gate voltage now. But if I change the drain voltage by a little bit, you can see that I'm going to get a little bit more current. The amount of current that I get will be proportional to the increment in voltage between the drain and the source. And if it's a linear characteristic like this, which is usually a good approximation, we can write the increment in current as the increment in voltage divided by the output resistance. The output resistance is just 1 over the slope of this line of this transistor characteristic in the output regime. So this is what we call the output resistance of the transistor. So now I can go back to my circuit. Some clever circuit designer has implemented a current source up here that has nearly infinite small signal resistance. But there's always a resistor here between the drain and ground associated with the transistor itself. That's determined by the slope of the IV characteristic in this saturation region where the current isn't exactly saturated. That's what we call R0 for R out. We saw in a simple circuit that the gain of this circuit is minus G sub M times the value of the resistor in the drain. Well, now the resistor in the drain is the small signal output resistance of the transistor itself. So minus G sub M times R out is the maximum gain that could ever be achieved. So the output resistance then is also a key figure of merit for a transistor. The higher it is, the higher this gain is. This gain is referred to as the self-gain. It depends on the transconductance of the transistor and on the output resistance of the transistor itself. It's intrinsic to the transistor. No matter how clever you are with the rest of the circuit, this is the maximum gain that you can get out of it. All right, so just to make this concrete, here is some CMOS technology from a few years back. Here are some IV characteristics, output characteristics of the N-channel device and the P-channel device. Let's see if we can figure out what the transconductance, output resistance, and self-gain are for this transistor. Well, the transconductance, we take the change in drain current for a change in gate voltage. So here between 1 volt and 1.2 volts on the gate, I get an increase in the drain current of 0.2 milliamps. I just divide the two, and I get a transconductance of 1 millisiemens per micrometer of width. So everything is usually quoted per micrometer. If I made a transistor that was twice as wide, I'd get a transconductance that's 2 millisiemens, right? Okay. If I look at the output resistance, I'll just take the slope of this line in the saturation region. If you pull numbers off of that, you'll find that the slope gives you an output resistance that's 7 kiloohm microns. Okay. So what that was, kiloohm micrometers. So again, we quote it this way. If the transistor is 1 micrometer wide, the output resistance is 7. If the transistor is 2 micrometers wide, the output resistance is 7 divided by 2, etc. Okay, what's the maximum gain, the self-gain? It's just a product of 2. It's going to be 7, all right? That's not high. You know, it's high enough that we can do some useful things, especially if we cascade amplifiers together. You know, this is one of the cascade amplifier circuits together. This is one of the reasons that for some applications, people will go to bipolar transistors. Self-gain tends to be much higher, you know, 10, 20, 30 times higher for a bipolar transistor. But this is adequate for many of our applications, and since many of our applications are using both CMOS digital and we need some analog to go on with it, we very often implement analog functions in CMOS. Now, if we look at self-gain versus scaling, one of the things that we will find as we understand transistor physics a little more is that when we make the channel length shorter and shorter and shorter, the output resistance gets smaller and smaller and smaller. So the self-gain gets lower and lower and lower. So you can see this, that if you plot the maximum self-gain versus technology generation, as the minimum channel length in the technology decreases, that was Moore's law scaling, the self-gain drops. So you will very often find analog designers not using the shortest gate length transistors possible, but using longer gate length transistors so that they can get higher self-gain. Right, now we also want to understand how fast the device can operate. What are the highest frequencies that the device can work at, and what are the limitations on the frequency of the input signal that can be amplified? Well, let's go back to our model. You know, our little model for the transistor, small signal wise, was that the small signal current was transconductance times small signal gate to source voltage, but also small signal drain to source voltage divided by output resistance. That's what we came up with. Now, we can draw a little circuit that basically just represents that equation. This circuit says that the output current is the sum of two quantities. One is this dependent current source, G sub M, times the input voltage. The other is this output resistance, the voltage across these two terminals divided by the resistance. So this circuit is just a way to visualize this equation. We call this circuit a small signal equivalent circuit of the MOSFET. Now, in a real transistor, there are also capacitors present. We know that between the gate and the silicon channel, there's an oxide layer and there's a capacitor that's there. That's really intrinsic to the function of the transistor. So there is a capacitor between the gate and the source. Now there are also other capacitors, and one of the important ones is there is a capacitor that is present between the gate and the drain. This is an undesirable capacitor. It occurs because there are fringing fields from the gate that overlap with the drain electrode itself, and that provides a capacitance, generally a much smaller capacitance, but it can be important in circuits, and it's important to recognize that it is there. So this is our small signal AC equivalent circuit. And if we analyze this circuit, we can understand how fast the device can operate. So a common measurement that is easily done is to measure the short circuit current gain. So what we would do is to connect to our transistor and a current source and vary the frequency of that current source. We do that at the input. At the output, we will short circuit the output. We do that by attaching a large capacitor across the output terminals. That will short circuit it to AC signals. And then we'll measure the AC current as a function of the frequency of the input current. And then we'll do a little bit of circuit analysis and determine what we have. Well, there's a node here that we can do Kirchhoff's current law at, and we can write down the current coming into that node. There's a current I out flowing into that node. We also have here a voltage V gate across this capacitor. The other voltage on the other side of C gate to drain is ground. So if we write voltage times admittance of the capacitor, we have another current flowing into that node. And then the current that flows out of that node is G sub M times VGS. So we'll have Kirchhoff's current law there. It turns out that if you put typical numbers in, this gate to drain capacitor is small enough that that current can generally be ignored to a good degree of precision. So we can simplify that equation. We can also express the input voltage in terms of the input current. We have a current coming in. At this node here, we see a capacitor to ground, C gate to source. We see a second capacitor in parallel with it that is also connected between the gate terminal and ground. So voltage is current divided by impedance. So we have two expressions here. We can put these two expressions together and we can solve for the output current in terms of the input current. What we're interested in is in the ratio of those two. We would call that ratio beta, the current gain. And if we divide the output current from the input current, we find that the current gain is G sub M, the transconductance, divided by frequency and the total capacitance. Okay. All right. So if we were to plot that as a function of frequency, you can see that this gain drops linearly with frequency. We typically would plot it on a log plot in decibels. So decibels would be 20 log base 10 of this current gain ratio. And if we do that kind of plot, well, we'd get a straight line on a log plot. You can see from this definition of decibels that if we increase the frequency by a factor of 10, we will decrease the gain by 20 decibels. So this line drops at 20 decibels per decade. If we extrapolate that to high frequencies to the point where the gain in decibels is 0, which means the gain is 1, then beyond that frequency, we don't have any useful amplification. So that is the maximum frequency possible that we could operate a circuit at. The rest of the circuit will generally slow down the operation of the circuit, but it can't go any faster than the transistor can keep up with it. So this maximum frequency, where the gain drops to 1, that's called the unity gain bandwidth product. That's denoted by omega t, and that is an important quantity for assessing the high frequency performance of a transistor. So we've deduced that omega t is G sub M divided by C total. That's 2 pi times F sub t. Omega is in radians per second. F is in hertz or inverse seconds. It's sort of easy to remember. G sub M is what makes the amplifier amplifier. The higher the GCM, the better. Capacitance is what slows things down because we have to charge and discharge the capacitor. So high capacitance is bad. So G sub M over C total is the gain bandwidth product. So the gain bandwidth product is a very important figure of merit for analog RF transistors to assure that we're going to be able to operate our circuits at the frequencies that we need to operate them at. So we have this F sub t. It is, insensitive to things like the gate resistance and the output resistance. It doesn't give us the full picture of how a realistic circuit that's configured in more complicated ways might operate. There is another figure of merit called F max, the maximum frequency of oscillation, or it's the unity power gain frequency. That requires the analysis of a different kind of circuit, and I'll just show the results here because Frequently, both numbers are quoted. Both numbers need to be high if we want to operate realistic RF analog circuits at high frequencies. Fmax is more sensitive to several of the parasitics that just don't happen to come into play when we measure FT. So both Fmax and FT are important figures of merit. So we've talked about three kinds of important analog figures of merit: transconductance, self-gain, and FT and Fmax. So those are relatively easy to measure, especially the first two. So they're commonly measured, and these would be the first figures of merit that an analog person would look at to determine whether this transistor is suitable for the application. There are other important considerations that you would then look deeper. There are issues like how much noise does the device add to the input signal. Device mismatch is important also. Device linearity. We want a linear amplified replication of the input signal. We don't want it to be distorted. So these are important considerations at all. Let me just mention why device mismatch is important. That's because many of the analog circuits are built this way in balanced pairs, source-coupled pairs of transistors. And in order for these devices to operate properly, we want both transistors on either side to have identical characteristics. Small differences in the characteristics between one and the other can degrade the performance of circuits like this. All right, let's wrap up. So we've just had a quick look at analog circuits and what's important in terms of transistor characteristics for analog circuits. Small signal transconductance is really important because it tells us it is a measure of the transistor's ability to amplify analog signals. Self-gain is also important. That brings in the output resistance, and the output resistance of a transistor is also important because it limits the maximum gain that will be available in an amplifier. And FT and Fmax are very important figures of merit because they help us determine how high in frequency we can use these transistors. Okay, other important figures of merit, if the transistor looks promising from these first three figures of merit, then we would look in more detail at some additional figures of merit. Okay, so that's a quick summary of what I hope you'll take away from this very brief look at analog circuits. So what's next? So we now appreciate a little bit about digital circuits and a little bit about analog circuits. So now we can turn to the question about device metrics. If I'm given a transistor, what measurements should I do so that I get a good indication of how well this transistor would perform in a digital application or in an analog application? And that'll be the topic of our discussion in the next lecture.